At the IBM Research Haifa lab, we are developing program understanding and transformation tools. The Business Rule Identification and Extraction, or BRIE project, applies these tools to the business rule domain. This is a demonstration of the current status of the BRIE project in October 2012. Ideally, we would like to be able to take code like this and color it like this in order to find the business rules in it. As you can see, this isn't trivial, since rules aren't always contiguous in the code, and they may be intertwined. Finally, we would like to extract the rules into a rule engine, such as IBM WebSphere Operational Decision Management. The scenario we will explore in the demo is that of a healthcare payer trying to extract business logic from its legacy claim adjudication system. This is a relatively small system, and for this demo we focus on two concepts: treatment payment and insured payment. Suppose we have the code loaded in a workspace and we want to search for business terms in it. We can use IBM context-aware traceability technology in order to perform an intelligent search over the code. In this example, we're looking for the term treatment payment. After performing the search, we can find results in several files. Let's look at one of them, master update. And there are 4 matches for this term that we're looking for, treatment payment, in this file. So as you can see, the first one is a perform statement for paragraph 3000, calculate treatment costs. And even though we use the term treatment payment in the search, because context-aware search knows that cost and payment are synonyms in this context, it will find the treatment costs paragraph, even though we were looking for treatment payment. And all the rest of the matches in this file pertain to the same paragraph in various ways. Context-aware traceability technology is a wonderful search tool, but now we still have to examine each result manually. The search has to be repeated for each term separately, but we may have a large number of concepts, each of which may be composed of several terms. In order to automate this process further, we built another layer on top of context-aware traceability technology to perform an ontology-based search in batch mode. This layer performs many searches and combines the results. It can show these results in various ways. This tree map shows the distribution of the combined two concepts in the modules of the application. Each module is shown as a rectangle and is further subdivided into paragraphs. For example, here you can see the test data module, which comprises this rectangle and is composed into several paragraphs. The size of each rectangle is proportional to the number of code lines, and the color strength represents the relative part of the paragraph dealing with the concepts. This immediately leads our eyes to the most relevant modules. We can see that some, but not all modules, have color patches. Test data looks the most promising, but obviously it only contains test data. We can investigate the others. For this demo, we are focusing on master update, right here. We can also show the distribution of concepts in modules or other units using a radar chart. This example is taken from a much larger code base and shows the distribution of 7 concepts in the code. We are experimenting with various ways of presenting this information. This type of visualization can help scoping projects by focusing attention on relevant parts of the code. In this example, you can see that there are several modules that seem unrelated to the set of concepts we are searching for. We are now moving from global search over the whole code to more local search, trying to find rule implementations and extract them. We can now drill down to the code itself. The sample XML file contains a representation of the 2 business concepts that we're looking for. In this preliminary interface, this has resulted in the generation of several files containing information about the distribution of business concepts in the code. we can choose the two files related to the master update file and see the results on the file itself. As you can see on the vertical ruler, there are a number of annotations in this file related to the two business concepts, each in a different color. For example, here are data definitions related to each of the two concepts. Here is code that goes to the database to get values relevant to one of the concepts. These two paragraphs are particularly interesting because they contain computation that is relevant to both concepts and combines them in some way. And this is the 3000 paragraph that we've looked at before. The code in this paragraph computes the total lab charges for an array of line items representing lab tests. This looks like a business rule that is a good candidate for extraction. We now move to precisely identify the rule and extract it. In every iteration, this code gets relevant information from a database. This happens in the paragraph called 2200 get lab provider. This shouldn't be part of the extracted rule, since the rule engine is not supposed to access the database directly. So the loop needs to be separated into two parts, one which collects the information, and another that uses this information to compute the total treatment charges. The second loop will be the extracted rule, which we can then transfer to the rule engine. In order to precisely separate the rule from the surrounding code, we use our patented fine slicing technology. We would like to find out all the code that is relevant to the computation of the total lab charges. What we can do now is mark this line and compute a backward slice. A backward slice of a program from a given point computes all the parts of the program that are relevant to that computation. These have now been marked, and as you can see on the vertical ruler, there are quite a few parts of this program that are relevant to this computation. In particular, you can see that the call to the 2200 paragraph is included in the slice because this is relevant to the computation of the lab charges. And here is that paragraph itself, and you can see the access to the database to get the information that is later used in the 3000 paragraphs in order to compute the total lab charges. The values that are used in this paragraph from the database are the physician found, network flag, and cost reimbursed %, which are different for each provider. In order to separate out the code, we need to remove from the slice the variable that it fetches from the database. We can automate this process by implementing a heuristic that says that any values from the database or other external data should not participate in a rule, but meanwhile we can remove these manually. Now we can compute a fine slice, which computes that part of the program that is relevant to the computation of the lab charges, excluding those parts that contribute to the computation of the three variables physician found, network flag, and cost reimbursed %. Now, as you can see, the call to the 2200 paragraph is not part of the slice, or rather the fine slice, and that paragraph itself has been now removed from the slice. In order to better understand this computation, we can look at more of this code in an unreadable font and see the full slice from the 3000 paragraph, which contains all of it, as well as a large part of the 2200 paragraph and other parts of the program, in comparison with the fine slice, which only has part of the 3000 paragraph, excluding the call to the 2200 paragraph. Our patented extract computation refactoring can extract the fine slice into a separate modular unit. In particular, it can split loops and create new data structures to carry information from one instance of the loop to the next. The implementation of this refactoring isn't completely integrated with RDZ, the Rational Developer System Z, yet, so at this point we can only simulate it. Part of this transformation is required the generation of new arrays to carry the values from the first instance of the loop to the second. Here you can see that the original loop, which got the information from the database and computed the total lab charges, has now been shrunk, and all it does is store the information that it gets from the database in the new arrays generated for this purpose. A call to a new paragraph, 3200, has been added, and this new paragraph contains the code from the original paragraph to compute the total lab charges, but instead of fetching the data from the database, it uses the arrays which were initialized by the previous instance of the loop. In order to understand this better, you can see the original loop here and the way that it has been split into the two loops. The red code has been added, and it has to do with the new arrays generated to carry the information from the loop on the left-hand side, which gets the information from the database and stores it in these new arrays, to the second instance of the loop on the right-hand side, which uses these values in the arrays instead of getting them from the database. At this point in the demo, the business rule has been extracted into a separate modular unit in the COBOL program. This may be sufficient for some clients. However, the final goal of BRIE is to convert the rules from COBOL into WODEM. This poses a number of challenges, mainly due to the different control structure of a rule engine and that used in procedural code. This part of the research project is still in early stages. At this point, I can show you the version of the rule we would like to be able to extract automatically from the extracted COBOL code. This is one version of the rule, which is invoked for each line item and adds it to a total lab charges variable. And this is another version of the same rule written in a more functional style, which may be more appropriate for a rule engine.